reactions are occurring, that kind of idea. Okay? So you should start wherever you think is easiest to start. Okay? Any ideas? Where do you think is easiest to start? Okay, the beginning's not a bad idea. Which beginning? Because you'll notice there's two places that we could start. We could go here or over here. Okay, so if we start at position number 1, what changed? We started with an alkyne, which has what formula? Okay, a lot of people still aren't comfortable with those abbreviations, so that's fine. Add that extra structure to it so that you know what's in there. If we look at the product of that, we've got our carbon. We still have hydrogens. So what changed as we went from our reactant to our product? We only added 2 bromines. So what species should we put in the middle? We need to put something in here that brings in 2 bromines. Okay? You'd have to know what reagent is going to be the best option for that, and in that case we're looking at bromine, elemental bromine, so Br2. Yes?
How does it maintain a double bond?
I was hoping you wouldn't ask that one. The exact ratios on that, you'd have to play very carefully. We haven't talked about experimental issues. If we add bromine to this structure, the odds that we only add a single bromine to a single acetylene molecule are pretty slim. More than likely, we'll see bromine add multiple times to one structure, okay, as a possibility. So as far as our yield goes, how much of this final product would I expect to come out? Depending on the exact ratios of the materials that I put into it, I might expect a lot, I might expect a little. If I only put 1 mole of this in and 2 moles of bromine, would I expect a very high yield of my product? The product drawn here. Okay, how many bromines are in my product? 2. If I add 2 molecules of Br2, how many bromines need to show up in my final product? 4. What are the odds I would end at this product? Very slim. So what we can do to sometimes control the outcome of an individual experiment is to control the exact amount of reagents that you're adding into it. Okay.
We can just let you put that's going to happen and just go from there.
Yes. So it's going to come down to what question is asked. If I left it blank with the product blank and said Br2 is added, you would more than likely say fully substitute or fully add, and all the double bonds disappear. In this case, because I've forced you into that position, that's what you have to run with. Yep. Okay, so we've done the first step. So what should we do now? So now again, we have 2 options. We can either continue on the path that we're on, or we can shift over to 2. Where should we go? Should we continue with the next step in that reaction, or go to our other beginning part? Okay. At this point, it doesn't matter. All we're trying to do is put more information in here. At some point, we need to do both of those if we're going to somehow get to the end of this reaction. Okay, so it doesn't matter where we end up going. Which place would you like to go to?
Left to right.
Let's do left to right. We have an alkene, and we add hydrogen, H2 with a palladium catalyst. Okay, what does that reagent do in the presence of a double bond? It adds hydrogen to our structure. Okay, that's where you would have to draw out your final product. There are a variety of ways that you could end up drawing this. I'll draw it the big, long, extended way first. Okay, with all of our hydrogens and our bromine all added in there. Right? That looks awfully cluttered. Could we simplify that? Yeah, what could we do? That was kind of a terrible angle there. Okay, shows the exact same result. Okay, that's up to you to decide what you want to write down. What I will probably end up writing down in my keys would probably be the simplest thing. Okay, and I'd probably even write down the more complicated or the bigger one, because I would guess that a lot of people would write that answer down. So to speed my grading, I would include both, so I know what I'm looking for. Does that make sense? So what happens now? Can we move to the next step? The next step for moving our left to right would then shift downwards. To do that downwards step, I need to know that I've got this and that, which I don't have yet. So I need to know what thing shows up in that box. That's why we have to go back to position 2. Again, we can go through and evaluate what's happening to our structure. Whoops. 2's too close. Okay, we've got the alkyne in the presence of NH2 minus is a very strong base. The alkyne was partially acidic, so what can happen? We do an acid-base reaction and we remove the hydrogens from the alkyne. What's the result of that? We didn't do anything to the triple bond, but we end up pulling off the hydrogens, so we end up with a lone pair on both carbons. Each carbon ends up being negative. Yes, that's highly unstable, and I'm not particularly concerned too much about that. Okay, the exact ratios on this, again, you don't need to be concerned about. Okay, what's special about that new species? It's negatively charged, which means it can act as a nucleophile or Bronsted-Lowry base, or even a Lewis base. Okay, all of those options. So we can now take that compound and interact it with our other species. If this species is negative, what do we need to find over here? Positive. Where's our most positive atom? On our carbons. Why the carbons? Because the bromine's electronegative, drawing the electron density away from the carbon. So we can go through and have this species interact. Okay? You'll notice extra pieces of information. It says use 2 of these, use only 1 of these. Make sure you take that into consideration when trying to draw your product. Okay? Kind of makes sense? So the idea is to slowly piece your way through it, one by one, until you can kind of progress forwards. You'll notice through the heart of this, there's a lot of empty boxes, okay? Which means you're going to have to start working your way backwards as well as forwards. Okay? Saw your hand.
Yeah, if you could just explain real quick why the 2 hydrogens would be eliminated from that.
They aren't eliminated. It's an acid-base reaction. That carbon, because of the hybridization on it, because it's now sp hybridized, is higher in electronegativity, that it actually pulls the electron density away from that hydrogen, which would generate H+, so we need something to stabilize that H+. That's where we bring in a strong base. The strong base will pull off that hydrogen.
Because there's 2 of them, there's 1 for each.
Because I put 2 base molecules in there, 1 for each one.
Got it.
Exactly right. Okay? So it was a little bit of a guide because there's a lot of boxes floating in the middle there. Let's move here to see if we can come up with something that we can work our way backwards to get some more information in there. What reactivity do I have in that structure? So when I'm looking for reactivity, I'm looking for differences in electronegativity or multiple bonds, pi bonds. Do I have pi bonds? No. So what do I need to look for? Electronegativity. Do I have any electronegative elements in that structure? Yes, I've got those oxygens. Okay. Taking a step further, those oxygens, are they in a standard structure? No, they're in a very strained ring. Such a strained ring that we end up calling those rings by a special name. What do we call them? Strange rings. Not a bad guess, but no. We've got epoxides. How do we make epoxides? You'd have to know your reagents. So you'd go back to your epoxide formation and say, what things make epoxides? We only talked about one reagent that makes epoxides. That was looking at your peroxy structures. The reagent that we're going to use, MCPBA. What does that react with in the formation of our epoxides? How would we know? We go back, we look up the reagent and figure it out. What does that reagent react with? Double bonds. Which means, what's our starting material? What has to go into this box? Something with double bonds. Is the sigma structure outside the epoxide going to change? No. So let's go through and draw that in. There's 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay. Where are double bonds going to be to form the epoxide? They have to be at the end. Because that's how our epoxide was formed. Okay. So you have to know the reagent to be able to do a lot of these types of reactions and these types of problems. Which means you need to be summarizing every single reagent we talk about. You should have it written down on a flashcard or a note card so that you're constantly reviewing these. Because if you don't know what the reagent is, how do you solve the question? You don't. Okay? So I know everybody said there was a lot of memorization. There wasn't memorization up to this point. At this point, you now need to actually memorize things. Everything else was looking for differences in electronegativity, okay, which in theory you already knew from previous classes. Okay? This is where the class gets a lot more difficult, because large portions of it now are coming down to things like this. Okay? This problem on its own is a lot more difficult than you can expect on the exam. You can expect plenty more of these types of questions in your homework. Okay? Because it's going to force you to go back and look at those individual functional groups and start to evaluate their chemistry. Does that make sense? Okay? I know, it's depressing. Or look at it as a great thing. Look at how far you can really progress by the end of the semester. You should be able to predict how to make virtually any organic compound. That's kind of cool. Whoop. Please. That's not that one. That's correct. That one is wrong. That's the error on the quiz. Click.
Oh, okay. It was just an error, not just like you put the wrong one in there.
No, it was a pretty big error.
Okay.
Yeah. Okay. So the quiz that you guys have is wrong as far as that question goes. Okay, so it's the bottom half of quiz 8. Everything else on that quiz, as far as I'm aware of, is fine. Okay?
All the other questions are good, it's just that number
It's
2.
just the bottom half of number 2, yes. Okay? Other questions on that?
Sorry.
You say that to me?
Yeah.
Oh, why?
Because you already said that.
Oh.
I was thinking that was the perfect one, so I wanted to follow along.
Oh,
I
no,
didn't
no.
realize it was just like wrong. Okay.
Yeah, it was straight up wrong.
I'm more comfortable.
Okay, so what other things did we look at on Tuesday? We had benzene with aromaticity. Okay, this comes back to those rules. You need to know the rules to be able to apply it. What I'll end up giving on the exam, okay, is ultimately going to be true-false questions. Okay, coming back and applying those rules. So given a structure, is it aromatic or is it not aromatic? True or false? Okay, I would then expect you to be able to tell me what rule, what piece of that information says that it's not aromatic or says that it's aromatic. Okay? The only way it can be aromatic is if you have all of those 4 rules valid. If one of those 4 rules is invalid, it's not aromatic. Okay? Questions about that? Those aren't any new structures on there. So should we do an example one again? Because we went through all of them before.
I'm still
Yes.
a little lost when there's the lone pairs
Yes.
and how that interacts with having the pi electrons and them getting moved around. I'm a little lost in the sauce with that. Yeah, on that one, how you have two lone pairs, two pi bonds.
So as far as deciding what lone pairs are possible or not, we could go through and do everybody, well, even that doesn't quite work for this. I'm going to say we could go through and draw resonance. Okay? So we could take this lone pair and shift it inwards. And we could draw the result of that structure. If we did that, if we did that, this carbon ends up having too many electrons, so what do?
We move it.
We move the electrons to that atom. God, why is it doing that? So if we draw out the rest of our structure, got our nitrogen, lone pair, double bond, and our lone pair up there, right? This is hydrogen, this is positive. Yep, agree? So what we've shown is that that lone pair is part of the pi system. We've done resonance with it. If we can do resonance, it's part of our pi system. Okay. What I was hoping is that we could say that works and the other one didn't. Can we draw resonance? Let's go through and draw it in a different color. We'll go through and say red. Can we do resonance with that lone pair?
No.
Okay, so if we drew it out, we'd get something that looks like yes? Everyone agree? Everyone see that? Okay. Is that a valid resonance structure?
No.
Okay, no. Why not? Why do you not like that resonance structure? Because that's a good answer. That doesn't work.
The locations of the pi bonds and the
Well, we still have two charges in our other structure. And what do you mean by the locations of the pi bonds?
they're touching each other, they would want to be spread out.
We can generate a structure that has pi bonds touching each other, like in this guy, where this is H2 and this is H2. That is a valid structure.
But when it's cyclic.
There you go. The bond angle there has to be 180 because that nitrogen is now sp hybridized. We're looking at a cyclopentane. The bond angle on a cyclopentane is nowhere near 180 degrees. So to be able to force that, either force the bond angle down, which puts a lot of stress on the structure, or trying to keep the bond angle open, we wouldn't be able to have the sigma bonds account for that. Those bond lengths would have to increase drastically. Okay? So we could look at it just being, it's an ugly structure, we don't like it, doesn't make sense. Okay? That works as far as you guys are concerned. For those of you that have want a broader understanding of why that doesn't work, we'll just briefly mention this. Where are these electrons held? I don't like that answer. We talked about why outside isn't a good option. Give me an orbital. Oh, I was going to bring a model kit. Dang it. It's not a p orbital.
SP.
It's sp2. That's where our lone pair is. Okay? Because of the 3 bonds around that nitrogen, or the 3 groups of electrons around that nitrogen. So if we go through, sorry, I really did mean to bring the model kit. That would make this easier to see. So let's go through and try and look at that structure and look at the electrons. So if we were going to draw that out, sp2, we're looking at what geometry?
120.
Trigonal planar. Okay, so there's our lone pair out there, and then there's our other carbon. Okay, where's our p orbital in this structure? The leftover p orbital. It's coming in and out of the board at you. Okay, so if we were going to draw that on, it'll look terrible, but we'd probably have something kind of like this, and the other half is back there. Okay, if we take this structure, let's pull that front carbon and lone pair up and out towards you. Should draw in more space. Okay, what happens? So we've got your nitrogen going directly backwards is the carbon. Coming up at you is the lone pair. Coming at you is the double bond. This is not how you draw a double bond coming at you, but I don't have a better way to do it. Okay, where's the lone pair now? Or sorry, the p orbital? It's now up and down. For these electrons to get into the pi system, they have to be in a parallel orbital to the p orbitals. Is it parallel? It's perpendicular. Because they're in perpendicular orbitals, they cannot share. They have to be in parallel orbitals. Okay? That's the stricter definition of why that lone pair is not available to do resonance. The other option is exactly what you guys did. The resonance structure looked ugly. So we'll say that that's not a good structure. Okay? Does that help with your understanding on when you can deal with those lone pairs?
Yeah.
So try to draw resonance. If you can draw a resonance structure where the lone pairs shift into the ring and it doesn't make a really nasty looking structure, those electrons are fine to count as far as your Rule 4 goes. Okay? Questions about that? So let's count it out real quickly. How many pi electrons are in this?
6.
We've got the lone pair, which we said we could do resonance with. We've got the pi bond, which has how many electrons?
2.
2. We've got another pi bond, which has 2, 4, 6 pi electrons. Rule 4 says we have to have 2, 6, 10, 14, one of those numbers. We've got 6. That rule is valid. Does that make sense? Okay. We then went through and ended really, really quickly with the mechanism for your EAS reaction. Okay, so we'll go back through that now. So to start off with, we picked an electrophile, and we picked a really nice symbol for our electrophile. We picked E. Positive. For our aromatic structure, we picked a nice easy one, so we started with benzene. And we said that this reaction ultimately, so I'm just going to draw a dashed line to our product, ultimately did a substitution reaction. So our product is going to end up looking like our benzene ring again. We don't want to get rid of the pi bonds because then it's not substitution. With our electrophile now attached to the ring and H plus as a side product. Okay? So that was our electrophilic aromatic substitution as the overall reaction on what occurred. Trying to put together the mechanism. Okay, so to go through and do that, we go back to our starting materials and we say, okay, which of those is the most reactive, the electrophile or the aromatic ring? Which one do you think is the most reactive at this point? Electrophile, why? It's what charge? Positively charged, which means to stabilize that positive charge, what do I need to find? Electrons. So we now move to the aromatic ring and try and find electrons. Where are there electrons in the aromatic ring? In the pi bond. So we'll take the electrons from our pi bond and we will share them with our electrophile. What does that produce? So now we end up going through and trying to draw out our intermediates and see what changes occur. Okay, did we do anything to the pi bonds on the bottom or the right? No. So what should we show up in our product immediately? Those pi bonds. The pi bond on the top. Okay, did we do something to that pi bond?
Yes.
Yes, we took the electrons and we moved them out of the pi bond and we moved them into a new bond. That new bond is formed between two atoms. So we're looking at either this carbon or this carbon. Is there a difference between those two carbons right now? Nope. So do we need to worry about where we put the electrophile? No. So we'll go ahead and just put it on one of those two. I'm going to decide to put it there. Okay. The electrophile just gained electrons, started positive, gains electrons, so it's now neutral. If we go back to our carbons, okay, the carbon where we added our electrophile, we took electrons away from it because we took the pi bond out, and then we put the electrons back into a sigma bond at that same carbon. So we take electrons away and put them back. The overall charge, neutral, no change. What happened to our other carbon?
Lost electrons.
Lost electrons, so it is now positive. How could you check your work? What's the overall charge in your reactants? Positive. What's the overall charge in your first step? Positive. What should it be? It needs to be the same. Every single step has to have a balance of charge. Okay? If it doesn't have that balance of charge, something is wrong. Okay? Is a positive charge a stable thing? Nope. So what we've got to do is try and stabilize it as fast as we can. Okay? So we need to find electrons nearby that can stabilize that charge as quickly as possible. Where are the most accessible, available electrons? In the pi bonds. So we'll go back to those pi bonds and we'll start to do resonance. We'll take the first one and we'll shift it over. We're going to move our electrons from the bond to the bond. What do we end up forming? So now we can draw out our reaction and see what happens to our structure. Right? Is this our final answer? No. What's wrong with it? It needs to have that charge. So we can go through and evaluate, and you'll find the positive charge needs to sit there. What's the relationship between structure A and structure B? They're resonance. The only thing we've moved is electrons. No atoms have exchanged place, no new sigma structures. We're looking at resonance. How do we show that it's resonance? The double-headed arrow. Have we stabilized our positive charge? We kind of made it a little bit more stable, but not all that stable. It's still there. So what do we need to do? We need to find electrons. Where are there still electrons? In the pi bond. So we can go back to our pi bond. Which pi bond do we want to play with? Either one, it doesn't matter. But if we use the one on top, what happens? We go back the way we started. We go back to structure A. So we'll deal with the other pi electrons, the new pi electrons. We'll move those from bond to bond. What happens here? Again, we can draw out the rest of our structure to see what things have changed. Is this our final answer? No. What's wrong with it? Charge. We need to draw on our positive charge. What's the relationship between structures B and C? Resonance. We show that again with our double-headed arrow. Okay. Is this structure stable?
No.
Why not? Positively charged. So what do we do? To find electrons. Where are most readily available electrons? In the pi bond. But do we have any more pi bonds? No. So if we go back and start drawing our electrons in our pi system, stabilizing that positive, that's great. That is happening, but that takes us back to structures we've already drawn. So now what we have to do is move outside the pi system. We have to find another source of electrons to stabilize it. So we could try and look to the solution. What things did we add to our solution? Our electrophile and our ring. What do we have in structure C? Our electrophile and our ring. So we can't bring anything from outside. There's nothing outside to stabilize it, which means we've got to find electrons somewhere else within the structure. If we can't find electrons in the pi bond, where do we need to go? True. I was going for sigma bond there, but you're right. We'll move to our sigma bond structure. and try and find the most readily available electrons in our sigma bond structure. Okay? That's where this gets difficult, particularly because I've drawn this too many times, and I decided to imply the hydrogens throughout this whole thing. So let's go all the way back to the beginning, or I'm going to go all the way back to the beginning at least, and show each of those hydrogens. Which will take some time, so you can kind of bear with me a little bit. I'll try and go as fast as I can. Okay? So when we go through and do this, we've got those hydrogens all the way around. And actually, I'm going to skip to just structure C. Which of those sigma structures, or sigma bonds, would I prefer to get electrons from? So what we're going to try and do is find the closest source. We've got a hydrogen right next to it. Right here, right? What if we took the electrons from that hydrogen? Could we move those electrons into our pi system? It's a tricky question. This goes back to the sp3 aromaticity thing that we were just looking at. Those electrons are in a perpendicular orbital. We cannot move those electrons in to stabilize the cation. Okay? So we could try and look at the bonds next door. Okay? That ends up breaking the structure. Okay? Breaking our ring open. That doesn't really help us out, and that also takes electrons away from a carbon, so we still get a carbocation. So then we have to go even further away, and we can start to evaluate the next three bonds. Here, here, or here.
You can't break E.
We don't want to break E off. Why not?
Because it's in the final product.
It's in our product. We just put it on the structure. Is that something we could still do? Yeah. That's why this step ends up being reversible. And we could draw an arrow going back the other direction. Notice it's not a double-headed arrow. It's two arrows. Okay? So we can eliminate E as a choice. Now we're looking at the next two hydrogens. Which of those two hydrogens is going to be the easiest to get electrons from? The one closest to the E. So we'll take the electrons out of that bond. I've been drawing it in red, so let's stick with that. Take the electrons out, and we'll move them into another bond. Okay? What's happened in this case? We'll get rid of all the color coding now. We've got E, we've got H, there's our double bond. What's wrong?
H plus.
Needs to be H plus. Why is it H plus? The electrons stayed in the structure, so hydrogen lost electrons. Okay, what's the relationship between structure C and D now? D is a product. Okay? So what arrow would we have to use in between? Could we show the double-headed arrow? No. Okay, this was an actual step. To further accentuate that so that we're aware that that's what's going on, or that's where our differences are, we can go through and put brackets around those three, because those three are resonance structures. They end up getting a special name. Okay, did we talk about the special name for them? Okay. Take a look at the bonds around the orange atom. What types of bonds are around that orange atom? Say that again a little bit louder. I think you said it. Sigma bonds. So what should we call these structures? Well, they've got sigma bonds, and their structures, we get sigma structures. These structures end up being critical to understanding the reactivity in an EAS reaction, okay, which is what we'll end up looking at when we look at the different parts of this mechanism. Okay, so we're going to keep revisiting these resonance structures, and I'll probably end up only drawing one of the set in each case, okay, further on down the line. Questions about this mechanism so far? Okay, now that we understand how the reaction works, or quotes understand at this point, okay, we want to try and change it. Okay, whenever we're moving through organic chemistry, we're trying to make our reactions go faster. okay, or with higher yield. Okay? To make a reaction go faster, what should we try and do? Okay, we could add heat. Heat's a good option because that weakens a lot of the bonds. Okay? But the problem with heat is that speeds all reactions, including the ones that don't make our product. So while heat can help us out, it also hurts us. So we want to come up with something that's more targeted to what we want. What else could we tweak? We could add something to help with the removal of the hydrogen. So it's starting to get at the idea. We're starting to look for something about the reactivity of our structures. What kind of a species would help remove that hydrogen? A base, because this species is acting as an acid. It's donating a hydrogen, so we could try and add a base. Okay? It turns out we actually don't need a base. That portion of the reaction is actually pretty fast. Why might that be pretty fast? We've got resonance here. What did we say was nice about resonance? Really, really, really stable. In our aromatic or in our benzene ring, we have aromaticity, which means it's even more stable. Do we have that here? No, we don't have aromaticity. Okay, we may have some resonance, but we don't have that aromaticity. So the hydrogen really wants to come off because we can restore the aromaticity and the uber stability of our benzene ring. Okay, so that step, you like the choice of uber? Okay, that step is pretty fast. Was benzene stable to start with? Yeah, so why would it ever react if it was stable to start with? It wouldn't. That's problematic. How can I make it react? So our big step, our clutch step in this, is trying to get this first step to occur. What did we say E was? Okay, it's an electrophile. So let's go ahead and write that on there in blue. We got an electrophile. What does the benzene ring act as? Electrophiles react with nucleophiles. If I want my electrophile to react faster, what could I do? Add more what? Add more nucleophile characteristic. Okay, what if I want my nucleophile to react faster? Add more electrophile character. How can I make an electrophile more electrophile character? How can I make a positive charge more electrophilic? I'm going to make it more positive. How do I make a nucleophile more nucleophilic? I need to make it more negative. Okay? And that's ultimately where all the reagents and the different reactions come from when we're looking at the EAS mechanism. We're looking at those two aspects, trying to make our aromatic ring more negative and make our electrophile more positive. If we can change them enough, we can force the reaction to occur. Okay? So ultimately all we're doing is making it more and more charged. Okay, so we'll take a look at speeding our reaction by tweaking the electrophile. So we want to make our electrophile more electrophilic. That means making the positive more positive. Okay, so I've got a couple electrophiles as examples here. Which of those is going to be the most electrophilic? Left, middle, right. Middle one. I don't like left or middle, right. We're going to call them 1, 2, and 3. I'll label them. Which is the most electrophilic? 2. Why is 2 the most electrophilic? It's the one that's positive. Which one's next? All of these, by the way, are valid electrophiles. All of them are valid reagents to use in an EAS reaction. 3 is being more electrophilic. What atom in that structure is the most electrophilic? This carbon. Why is that carbon electrophilic? Chlorine does what? What's the relationship between chlorine and carbon? Chlorine's more electronegative, which means where those electrons spend most of their time? On our chlorine. What else is attached to that carbon? Oxygen. What's the relationship between carbon and oxygen? Again, more electronegative. A lot of electron density is being pulled away from that carbon, which means that carbon becomes very positive. Okay? So we could then go through and rank this, and we say most, will be our second, and this would be our least electrophilic. Okay? I said all of these are valid electrophiles. We need to somehow make them more electrophilic.
Why would one be electrophilic at all?
That's a good question. So let's take a look at one, because that's going to help us out see what's happening with one of the reagents we can add to tweak this. Okay? What's special about bromine? What do you know about bromine? It's a halogen. Keep going. What did you say?
Large.
Likes one bond. Way to jump in on the answer. It's large. Why is it being large a big issue? What can you do with the electron cloud? Yeah?
They're not gonna wanna be near each other, so.
So you could see them trying to push away from each other, but that bond is nonpolar. We would expect the electrons to split, I think it's homolytically, meaning each of those electrons goes either way. That makes neither of them charged. So we don't want that. But what happens if I say bring in something, I don't know, something positively charged? What's a good thing that's relatively positive charged from our periodic table? Okay, I like the sodium example, right idea. Hydrogen's not a bad option, but that's also not, that actually does work as one of our catalysts. We can add a metal. What's special about our metals? They're positively charged. If I bring that metal up near this bromine, what does that bromine start to do with its electrons? Particularly if that metal is positively charged. It needs to share its electrons. So it starts to share. How many bonds can bromine have? 1. How many bonds does it have now? 2. So what ends up happening to the bond? Those electrons go towards our bromine. What happens to this bromine?
It becomes positive.
It becomes positively charged. Because I've pulled the electron density away from that bond. We can do that with bromine because it's so large. That large cloud means it's easily polarizable. We can pretty much push those electrons around to do whatever we want them to. If it was a small structure like hydrogen, we couldn't do it. Okay? Which is why when we go back to addition reactions with hydrogen versus bromine, hydrogen required a catalyst to do an addition reaction. Bromine did not. Why did bromine not? Because it's polarizable. What was your question?
I was going to say, not that it matters, but would the electrons always go with the one that shares?
Yes. Because that's where the electron density is getting pulled. So the electrons have to go that direction. Iron's not going to be particularly stable on its own, so what we end up adding, in this case, would be iron tribromide. We actually call it something else. But that species, again, if we take a look at that iron, what kind of charge would you predict that iron would have? Even if you knew nothing about what charge this metal should be?
Positive.
Should be positive. Why? Bromines we know are very electronegative. 3 bromines around it, electron density is going to start to pull towards that iron atom. Okay? So what we can end up doing is adding a secondary species that helps with the reaction, changes the mechanism slightly. What kind of a species helps a reaction go forwards? A catalyst. So when we're looking at electrophiles, what we can do is add a catalyst to help speed our reaction. Okay? And that's what we would end up adding to make them more electrophilic. Is that catalyst is going to somehow try and shift electron density away from whatever center we've got, making our electrophilic atom more electrophilic. Okay? So we can end up with a variety of different electrophiles. We can get Cl+, R+, and then even this last one down here, which we can refer to as, which I'll refer to later actually, as the acylium ion. Where do we get our electrophile Cl plus from? It's still going to come from, I'm going to regret drawing this, but we'll see. We still have to put it in there in such a way that we can generate that positive. If we added HCl, would that be a good source of Cl plus? No, why not?
Because chlorine would just take the electrons.
Chlorine's going to take the electrons away from hydrogen. So we have to bond that Cl to something that it can't take the electrons away from, like Cl. So how do we get Cl plus? We add Cl2. And instead of using iron tribromide, we can use iron trichloride as our catalyst. And what happens is the electrons on the chlorine start to share with that iron, and we end up with this really goofy looking intermediate. That chlorine really doesn't want to be positive, so what does it do? It steals the electrons back. Whoops, drew that a little too far. And we end up with our chlorine electrophile. Okay? How about R positive? So R is going to be anything with a carbon. Let's go back one. How can I get some carbon structure to be positive? So if R in this case just equals carbon, how can I get a carbon to be positive? I need to put something next to it that is electronegative. So I could add a halogen. How else could we get a positive? No, never mind. We'll leave it at that. We'll just add a halogen to it. That makes it positive. How can I make that carbon even more positive? I want to try and take more electrons away. How can I get that halogen to take more electrons away from the carbon? I want to add something else, just like we did up here, to start to pull electrons away from our halogen. What do we end up adding? This is where you get aluminum chloride. What's special about aluminum? Positive.
It's very lightweight.
It's a metal. Same thing as iron. Okay? So we end up with very similar properties. Aluminum has even more particular characteristics, but we're not going to worry about those. Again, we can start to share electrons with that aluminum. We end up with a goofy looking intermediate where our atom X is charged. So what does that halogen then do? It steals the electrons, and ultimately we make our positive electrophile. Okay? Yes?
Would the aluminum be negatively charged? Like it is
Yeah, yes.
And the same with iron?
Yes. Because that took extra electrons in. So in that structure, in fact, I should have put the negative charge earlier. As soon as it accepts electrons, it needs to be negative. Okay? The last one, probably one of my favorites just because I think it's funny. Anyone know what this one's called? It's kind of silly.
Really excited this chemistry
RCO
joke.
plus?
It's a psyllium ion. It actually is. It actually is. That's actually what you call it. It's a psyllium ion. Okay? So let's go back and look at that structure. Which atom do you think is the electrophile in that case?
Do you have a t-shirt that says that? Like, I'm silly.
That's not a bad idea. I could do that.
Maybe like 5 people would laugh at that.
As long as I could wake up in the morning and look in the mirror, that's all I would need. So, which atom is our electrophile in that case? Oxygen is positively charged. Is that our electrophile? What's one of the things missing from this oxygen right now that should be on there? It does have a lone pair. Does it have another one? No. 3 bonds, it has 1 lone pair and a positive charge. Can that oxygen act as an electrophile? To act as an electrophile, it must accept electrons. Does it have its octet satisfied? Yes. Can it act as an electrophile? No. Okay? So even though it's positively charged, that's not our electrophile. Where is our electrophile? Nope. Went a little too far away. It's our carbon. The electrons in that triple bond will shift out towards the oxygen, making that carbon very, very, very positive. Okay, there's our electrophilic structure. Where did that come from? Well, that's where we saw our structure already. We already saw that as an electrophilic species. That was this guy. Remember from the previous slide? And what we can end up doing is adding aluminum chloride. Again, our electrons share. We end up forming that goofy looking intermediate. That chlorine really doesn't want to be positive, so what does it do? It takes the electrons away from the carbon, and we end up generating the positive charge. To stabilize that positive charge, I need electrons. Do I have electrons, say, on that oxygen? Yeah, so we can move those electrons in to form. Yay, someone said it. Okay, to form our psyllium ion. Okay? So we can end up changing and tweaking our electrophiles depending on the different reagents we use. Okay? So you need to know what each of these things are and how each of these things can act as electrophiles. Okay? We can look at, instead of adding catalysts, we can add Bronsted-Lowry acids to our reaction. Okay? The first one is kind of a tricky one. What we can do is take nitric acid and sulfuric acid. Anybody know which one's stronger? Sulfuric is a stronger acid. In this case, it's really, really odd. What role does nitric acid play in that first step? What does it do? Whoops, sorry. What changed about nitric acid? So we're looking here to here. It added a hydrogen to it. It accepted a hydrogen ion, meaning that species acted as a Bronsted-Lowry base. A strong acid can be made to act as a base. Nitric acid in this case is doing so. So what ends up happening, our lone pair on one of those oxygens shares with our hydrogen. The electrons in that bond shift over to a sulfuric acid. We generate this unstable intermediate. Okay? That oxygen doesn't want to be positive, so what does it do? Steals electrons from that bond. We end up forming water and the nitronium ion. Okay? The nitrogen in that middle portion is positively charged. Why is it positively charged?
It's 4 bonds.
It has 4 bonds. Okay? That one is probably one of my favorite electrophiles, just kind of throwing that out there for exam time. Okay? Why might I like that one a lot? You would think names, but no. Comes back to that nitric acid. Making a strong acid act like a base, I think that's kind of cool. Okay? So that's one of the reasons why I'll pick that one. Probably is almost guaranteed is going to show up on your exam. Okay? The next thing that we can do, which I don't particularly like, but it's the same kind of idea, we can take sulfuric acid and react it with itself, and it can generate another electrophile. Okay? So you'll see questions on that in the homework, but I won't ask you questions about that. Yes?
So which one would we see that as a reagent? We see the H3.
So if this was in a reaction, you wouldn't see the NO2 plus. So if I said I wanted to do this reaction, put the NO2 on there, what reagent would I put in here? Is that what you're asking?
Yeah.
What you would likely see, and it would again depend on the question asked, you would see HNO3 / H2SO4. Okay. If I asked you to provide a mechanism, I would say NO2+. Anytime I ask you to provide a mechanism for an EAS reaction, I'll tell you what the electrophile is. I don't expect you to go through and draw out extra mechanistic steps for the electrophile. Okay. The last thing that we can do with our Bronsted-Lowry acids is way down in this lower case. What type of reaction is happening here? It's the first half of, not quite SN1, but right idea. You're getting to the mechanism names. If I made this a Cl, ultimately right idea again, we would end up with this, right? What did I do to translate from here to here? Substitution means something came off of my initial structure. Did anything come off? Addition. Okay, we added hydrogen and chlorine. Okay, in this case, we're adding sulfuric acid. Why does that give you a different result? Sulfuric, or the sulfate ion, is a terrible nucleophile, which means it's not going to do that final addition step. So what you're left with is that carbocation. Why is that helpful? We now have a positively charged species which can act as an electrophile. Okay? So these end up being the electrophile choices that you can see with an EAS reaction. So if you look at the practice quiz, the question number 1, the last 2 questions on the far left, are all EAS type reactions. You're starting with a benzene ring, and I give you 2 reagents and want you to predict the product. Those reagents are generating one of these electrophiles. Okay? So you need to use that information to predict what your product ends up coming out as. Okay? So, we just looked at speeding our reaction by looking at the electrophile. The other option is affecting our nucleophile. Okay? How can we make our nucleophile more reactive? What do we need to do? Make it more nucleophilic. To become more nucleophilic, what do we need to do as far as charge? It needs to become more negative. So we have to somehow put more electron density. Let's focus in on the benzene ring down below. I have to somehow put more electrons into this structure. So with the electrophile, I could add a catalyst to help suck electrons out. Can I somehow put more electrons into this structure? Are the octets satisfied in that compound? Yes. Which means, can I put more electrons in? No. None of those atoms can exceed their octet, which means I cannot speed the reaction by making our nucleophile more nucleophilic by adding a catalyst. What I have to do is change the structure. The structure must physically change, okay, to adjust my reaction. So what I've gone through and done is changed that reaction. Okay, at this point, we don't care about how we did that. I'm just telling you that we've changed it. What's changed? I have atom X. What can you tell me about atom X? Okay, yeah, it's going to work. Has a lone pair, and we're going to broaden our definition a little bit. Not only does it have a lone pair, it has more electrons than a hydrogen atom. How many electrons does a hydrogen atom have? 1. Okay, be careful, it's not a hydrogen ion. Okay, how does that affect our reaction? Okay, everybody's favorite. What can we do with those electrons? We can move them. Where should we move them? How many bonds are there to atom X right now? Only 1. Where do I move electrons? Through bonds. So, where should I move the electrons? How about into that only bond that we can move it to? Okay, which means I've now formed what kind of a bond between that atom X and a carbon? A pi bond or a double bond? How many bonds would that carbon now have? Too many. So what do we have to do? We have to break a bond. What bond would we break? We would break a pi bond. Oops. So we'll take this pi bond and we're going to break it, but we're going to move it, instead of going bond to bond, bond to atom. We want to try and limit the motion as much as possible so that we can cover all of these soon-to-be resonance structures. What's the result? This carbon now has a lone pair of electrons, and then we still have the double bonds everywhere else. Is this my final answer? No. What's wrong with it? It's missing charge. What charges is it missing? It's missing a negative where? Carbon with the lone pair is now negatively charged. Is it now done? The atom X now needs to be positive. Okay. How does this affect my nucleophile? Well, we're looking at the aromatic ring acting as a nucleophile. It has to have electrons to donate. What charge did I just put into the ring?
Negative.
Negatively charged. The positive charge, if we looked at just a aromatic or a resonance structure of our aromatic ring, if we did something similarly here, we could do something, whoops, we could do a negative and a positive. Okay, yeah, we've got a negative, but we also put a positive charge on the ring. So that kind of cancels itself out. If we look at our top case, we've put a negative charge on the ring and no positive charge in the ring. So what does that mean about the reactivity of our ring now? It's more reactive, it's more nucleophilic because I've put electron density on an individual atom. Okay? What position have I put electron density on? So how many of you remember Tuesday? You're actually right. It's the 2 position, which equals ortho, which equals O. You weren't here Tuesday. That would explain.
He was. She was.
Oh, no, that's right. You were. Never mind. I forgot you were missing today. Okay? If you continue to do resonance, any ideas where that electron density is also going to sit? As a hint. You'll also find it there. And you will also find it here. The 2, 6, whoa, don't write it there. The 2, 6, and 4 positions. 4 was our para position. Okay, so now we can get super creative and come up with a fancy name for this. Okay, we've now increased the speed of the reaction, or we activated the ring by putting atom X attached to our structure. Okay, so let's think transformers. What name are we going to come up with? We'll call it an activator. You were close.
That's not even
I didn't say it was one of their names.
No, it's not about transformers.
So we're looking at an activator. So atom X counts as an activator. Okay, taking a step further, what other information do we know about the reactivity of this new benzene ring? Where is it going to be reactive? Where would I expect the electrophile to substitute? Where's the electrophile attracted? The electrophile is attracted to negative charge. Where's their negative charge in this structure? 2, 6, and 4, but we don't like numbers. Ortho, para, director. Director. So that when we run the reaction, our electrophile is directed towards the ortho and para positions. So if I was going to say, do this reaction, let's give you an example here down below. I take too long to talk, by the way. I wanted to cover more information. Is that good or bad that I didn't cover more information?
Great. I'm still stuck on activator.
They see, I was there. I told you. If we take a look at this structure, and I'm going to react this now with Br2 in the presence of FeBr3. What's my product going to look like? Ooh, not like that. Still going to have my benzene ring. I'm still going to have my NH2. Where should I put the bromine? We'll have H plus come on. Either to the O or P positions, ortho or para. Drew this terribly. We'll actually see it at the para position. We'll talk about that why later. Give me a break. Okay, so we've got an ortho-para director because of the nitrogen, which means when we do our reaction with the electrophile, in this case Br+, the bromine will substitute either at your ortho or para positions. Okay? Does that kind of make sense?
So the ring is the director?
So the ring is not the director, it's the atom. Atom X. Atom X in this case is nitrogen. It's the atom immediately attached to the ring. Does this nitrogen have more electrons than a hydrogen atom? Yes. How do you know that? It has a lone pair.
So that's the director, then which one's the activator?
This is an ortho-para director and an activating substituent.
Oh, same thing.
Yes.
Wouldn't it go to the 1 or the 6, or the 2 or the 6?
Okay, fine. Since you asked. What we're looking at in this reaction is the electron density in that ring. Yeah, we can do it here-ish. We have to look at these electrons coming out to react with our electrophile. Okay, to react with E+. Right? What do the electrons have to get by if they come by from that double bond? Our activating group, which had lone pairs. What happens when our double bond electrons try and get by those electrons? They go back. What happens if we look at our para position? What does it have to get by? For all intents and purposes, nothing. So which position is more active? The para. Even though it directs to both the ortho and para positions. When would you expect to see an ortho product show up? Where would you put the bromine if instead of that structure we started with this? Okay. Not only is there more electron density at the CH3, is there an atom that we can substitute at that position on the carbon or on the ring? What do we do in our substitution reaction? We substitute for hydrogen ion. Is there a hydrogen attached to that carbon? No. So can I do a substitution for a hydrogen at this position if there is no hydrogens? No. So where does our bromine go? Go to one of our ortho positions. And it would be either or. Okay? So, what I'm going to kind of leave you with is just a little bit on the slowing the reaction down. So I want you to be looking at this. What happens if instead of atom X having a bunch of electron density, atom X looks like this? What's special about atom X in this case?
Positively charged.
Go more generically. Comparing it back to the hydrogen atom. If atom X has less electrons than a hydrogen atom. How do you get less electrons than a hydrogen atom? Has to be positively charged. Okay? So if the atom immediately bound to the ring has a positive charge, that changes the characteristics of our reaction. I'll draw out that mechanistic step here and give you your fancy transformer names. I've decided they're transformer names. We can draw the electron density from the ring going to the atom X. Atom X no longer has electrons to donate in, so the ring has to shift electrons. We end up with a very similar looking structure, except what happened to atom X? It was positive and now gained electrons, so it's neutrals. What happened to this carbon? It's now positively charged. What we'll end up finding when you draw out the rest of the resonance structures, which I'm going to ask you to do, you'll put positive charge at the ortho and para positions. Okay, if we're going to look at the speed of this reagent reacting versus our last one, would we expect it to react faster or slower?
Slower.
Slower because our ring acted as what in our mechanism? Begins with an N. Nucleophile. What does our nucleophile need to have? Negative. It needs to have electrons. Do we have electrons at the ortho and para positions? No, we lack electrons. Those positions cannot react because there is no electron density there, which means our reaction slows down. Okay, what's the only position left for it to react?
The ones we don't know.
The other ones.
The other one are meta positions. Okay, which would be the 3 or 5. So if atom X has less electrons than hydrogen, transformer names, deactivator. Why would it deactivate? Doesn't have the electrons. It slows the reaction down. Where should it direct? We get a meta director. Okay. We'll walk through that one slower next Tuesday because I'm pretty sure we're out of time there. And then we'll go through a bunch of examples, and that'll probably be the end of Tuesday's lecture. Thursday is going to be your aldehydes and ketones.